Okay, fine. This is the bottom part iron carbon diagram, and we know that this is alpha. This is alpha. This is austenite gamma. This is alpha plus gamma, and this is your main phase alpha plus Fe3. If you see. Is it fine? And this one you can extend it, and finally you can take it like this. And this one. But eutectoid composition is this one. If you take this composition, this is 0.76 weight percentage of carbon, and below this hypo, above this hypo. The question was, if you have the steel here, for example, take the steel of this one. This is any composition beyond 0.676. So this is hyper. Hyper-eutectoid steel. So we have to go to austenitizing temperature. That means this is what line? If you remember, this is the critical line. ACM. What is ACM? CM means cementized and A means arrest, right? If you remember. That is the upper critical temperature for hyper-eutectoid steel. Upper critical temperature for hyper-eutectoid steel. And this line is A3. This is upper critical temperature for hyper-eutectoid steel. Right? Because above this everything is austenite. So that's why that is the upper critical temperature. And lower critical temperature is this one. This straight line, eutectoid. A1. But the question was, if you have a hyper-eutectoid steel and you want to do annealing, then what should be the predetermined temperature? That was the simple question they asked me. So, since you people don't know the answer, so you will tell what? Above ACM you need to hit, of course. But the answer is wrong if you say above ACM. The question is, it is annealing. If they asked about normalizing, then that is fine. Listen it carefully. We will discuss that in the coming lecture. What is annealing? What is normalizing? Annealing means furnace cooling. Normalizing means air cooling. That is the difference. You need to austenitize the sample, then you cool it in air. Then it is called normalizing. If you austenitize the sample, you cool it inside the furnace. It is called annealing. So that means annealing is a very slow cooling. It will take maybe 24 hours or more than that also. Depends upon the cooling rate of the furnace. Okay. They just switch off the furnace. But air cooling means you take it out and put it in the air. Cooling rate will be very fast. Maybe after half an hour it will cool to room temperature. Or maybe in 13 minutes, 15 minutes, depend. Size of the sample also matters. So annealing. That is furnace cool. And furnace cool is a very slow cool. So what will happen, I told. Suppose I am talking about the microstructure. Suppose I am talking about the microstructure, let's see. So, this will form like this. What are these? Sorry? What are these? These are lamellar structure. Cementite. One band will be your cementite, one band will be your ferrite. Cementite and ferrite. You will see that in this composition, you have alpha and cementite, right? Okay? But this point is talking about this weight percentage of carbon, but the phase will be what? 100% perlite. So like this kind of structure. But you have chosen a steel above that. So that means it will be having perlite. This is one boundary and another boundary is Fe3C. So perlite plus Fe3C will be there. Okay. And in this composition you have ferrite plus perlite. Okay. These are the two boundaries, but I am talking about this one. So you have perlite plus cementate. So perlite by default will form, and perlite means alternate layer, you know. One band will be of Fe3C, one band will be of ferrite alpha. Suppose you are talking about this band is suppose Fe3C, let it be. So that means this white portion is of alpha. Okay, this band is Fe3C, this band will be alpha, like this. Okay, and this band will be inside the grains. Can you see how many grains? We have 3 grains. I have chosen 3 grains here, right? And these are what? These are grain boundaries. Perlite is done. Now cementate need to form, of course. So cementate, I told it is, if only cementate is formed, it is a precipitate, carbide. It will form on the grain boundary. So once suppose one cementate start forming, let me change the color. Suppose one cementate will form like this here, 10 degree, and another cementate forms like this. It precipitate now, but cooling rate is very slow. So since cementate won't precipitate, it will start forming along the grain boundary. So it will spread like this. It will start spreading like this. So entire material, if you take the cross section anywhere, you will see that entire grain boundary is having cementate only. Completely white portions will be there. I don't know, you have seen that in physical metals lab or don't know, you can ask Ratnakar, and I want to see hypereutectoid steel. You will see that along the grain boundary, white layers of thing will be there. That is nothing but cementate layers. So entire grain boundary is cementate, and cementate nature is highly brittle. So what will happen? A single crack will form at the grain boundary. It will easily propagate through a easy path. Easy path is your grain boundary. So entire material will fail. You don't want that actually. Okay, you understood my point? So why this is happening? Because cementate is forming preferentially along the grain boundaries, and it is growing actually. Why? Because of slow cooling. Sufficient time is available at high temperature, so it is growing. But if you cool it fast rate, cementate will form, but it cannot grow. So there will be a discontinuous cementate will form. One cementate will form, there will be a gap, again a cementate may form. There will be another gap, so discontinuous cementate is fine at least. But if cementate is continuous along the grain boundary, it is very bad. One crack may fail the material, a single crack. Because crack always try to flow in a easy path, a less resistance path. Less resistance path is the cementate network, which formed along the grain boundary. You understand my point? So slow cooling means network of cementate will form along the grain boundary. That is the reason why we never go above SEM. We will do just here. Here. Technically we should go above SEM, but we are not going for annealing. We are doing annealing in between SEM and A1. This is your temperature for austenitizing. But you will not get 100% cement, or you will not get 100% austenite. You will get what? Austenite plus gamma plus Fe3C. This is the reason. No? So what will happen? Whatever Fe3C is there, it will not transform. It will stay there only. Only whatever perlite is there, that is becoming what? Austenite. Again that will become perlite. Do you get my point? Or so there will be no change to cementate. Cementate will be there during high temperature. Again at room temperature it will be there. Only the perlite will become austenite. Again same austenite will become perlite. So no issue. But if you are going above ACM, then everything, the perlite and the cementate will become austenite. And when you cool it, some austenite will become perlite, some austenite will become cementate. And that cementate will form along the grain boundary. Okay? And they will grow because of very slow cooling. But if you talk about normalizing, listen carefully. Then you can go above SEM. That is the difference. Why? Because normalizing is a very fast cooling. Just you do austenitizing, take out your sample and put it in the air to cool it. So no sufficient time is available because cooling rate is very fast. So some cementate will form along the grain boundary, that will be discontinuous. Discontinuous means like this maybe. I am not drawing the entire diagram, but just see. that will form like this. See, there will be some gap. This kind of cementite will form. There is no connection between each cementite, no network. So that was the question actually they asked. So this kind of question also they will ask during interview. Heat treatment is a very important subject for placement. Listen carefully. Anyways, is it fine? So, okay, let me tell you about what kind of question you are going to get in the exam. So one question will be, suppose a steel will be given with a particular composition. So the first bit one will be, what should be the predetermined temperature? You need to write and you need to justify that. Second question will be, what should be the holding time? Fine. Holding time, you know, it depends upon what? Already we discussed that. Thickness, dimension, many things are there. Alloying composition, so you need to write, justify. Fine. And finally, what should be the cooling rate? This is kind of question you are going to get in the mid-semester. Question is not just a tricky question, but simple question. If you understood the concept, you can write it. This guy, you understood, this is the question, this kind of question you will get. Okay, iron carbon diagram, any confusion you have, or it is fine at least? So, we'll talk about properties today. Properties, right? Mechanical properties. Mechanical properties. So, first property, I can write ductility. So, what is the meaning of ductility? Can you tell me? Stretchability, okay. Stretchability. Integration under the plastic deformation. In that way, it's also fine. You are saying something. So, this is the first time we were operating on. Okay, these are school definitions. Maximum strain. Okay, anyways, how to measure ductility otherwise? Can you tell me? What kind of test we have to do? Now, what kind of test we have to perform to know the ductility of any material? Tensile test. Very good. So, can you draw the diagram of a tensile specimen at least? Can you draw it? Tensile specimen. Can you draw it? Just draw the diagram of a tensile specimen. There is no curvature, but it should be. There should be some curvature.
Dog bone sample.
No, I don't have to. There are sharp edges. How should I sharp edges? We need to do tensile test to know the ductility and strength basically. Anyway, so the test will be tensile test, and of course you have a specimen that means not good diagram, but at least this is fine. So this is a tensile specimen, right? So in this tensile specimen, what is the most important component in this? Total is called total length, no? From one end to another, it is called total length, fine. And next length will be. No? Hello. The most important part is the center part. That is called gauge length. Okay? Because during the test we need to study on the gauge length part only. We have to see the change in cross sectional area and change in the length in that region only. We are not considering the entire length. We will consider how much length has increased in the gauge length, how much cross sectional area have reduced in the gauge length. These are 2 points. We have to check cross sectional area or we have to check the length. That will talk about your ductility at the end. So that's why people call ductility is nothing but total percentage elongation. If somebody will ask to tell me the ductility of any material, just tell him that we need to perform a tensile test. After performing the tensile test, we need to find out percentage total elongation. Okay? Or percentage reduction in the cross sectional area. See, when the length will increase, the cross sectional area will decrease, right? Either you find out the percentage decrease in the cross sectional area or you find out the percentage total increase in the elongation. But these two are fine. So what is the formula? Anybody remember from the physical metallurgy class? Formula for percentage elongation. Ln? Yeah, okay. Final length minus initial length divided by initial length. Initial. That is called percentage elongation. If you can find out, you can tell the ductility of the material. If it is very high, it is more ductile. If it is less ductile. Okay, fine. So gauge length is means from this region to this region. That is the gauge length. This is called total length. This is called reduced length from here to here. And this is the gauge length. This much is gauge. It is determined by percentage that is how much? Final L1 minus L0. This is called percentage elongation. Final length, because after elongation, final length is higher, of course. L0 is the initial length divided by initial length. You can find out. Similarly, percentage reduction in the cross sectional area, how you will calculate it? Initial area minus final area divided by initial area. Very good. Because initial cross sectional area will be more, higher. Final cross sectional area will be less. Percentage means into 100, of course. Yeah, percentage means into 100. This will be. Anyway, next is strength. Again, to know the strength, you have to do tensile test. Tensile test will tell you about the strength of the material. So, what are the different strengths we can measure by using tensile test or by doing tensile test? What are the three different strengths? Yield, UTS, and fracture. Very good. One is yield strength, one is ultimate tensile strength, one is fracture strength. Right? Very good. And the sequence will be in increase. It will be increasing order and of course like this. UTS will be the maximum. Okay. Most of the chance. Always. Actually always. Then it will be greater than basically fracture strength. And YF. Toughness, same, you need to perform a tensile test also, you can obtain the toughness. But it may not be exact value, but it will give you some approximate value. What is that? Area under the curve. Area under the curve will give you the toughness. Very good. Then resilience. Same tensile test also can give you the resilience also. Area under the elastic region also. Very good. Area under the elastic region curve is the resilience. Okay. Very good. So if I am plotting a curve between engineering stress versus engineering strain, because this kind of plot will obtain by doing tensile test only. Okay? Because most of the case tensile test will give you load versus displacement curve, but most of the machine nowadays they will directly give you the stress versus strain curve. So there is no issue. Otherwise, earlier days they used to get load versus displacement. Then you need to convert it into stress and you need to convert it into strain. Okay? But stress versus strain curve for a ductile material. Can you draw it? The first, this will go rise like this, and you will get a point that is called proportionality limit. Right? Proportionality limit means what? Up to that value of stress, stress is proportional to strain. That is called proportionality limit. Stress is proportional to strain, right? Up to that load or that stress, this value. Then it will go up further and finally reach another point, for example here. That is called YS, yield strength, or yield point or yield strength. Then finally, suppose this will move like this and fall and finally fracture. So this is YS, this is UTS, and this is it just I'm doing some change here. Here. See, this is your yield strength because this is stress axis, fine. This is the UTS, this much point, and this is your fracture stress. What I show you, UTS is greater than, fracture stress is greater than YS. So now, these are the three strengths also: yield strength, ultimate tensile strength, and fracture strength. So what is exactly strength now? Strength exactly means this is a stress versus strain curve, and plastic deformation is happening. That means permanent deformation is happening in the material. Permanent deformation is happening means material is getting elongated without any fail, basically. So during the elongation, see how tensile test is done. In tensile test, one end will be fixed and one end it is pulling the material. In this like this. So this end is fixed, this end it is pulling, continuously pulling. And what kind of like data we are giving to the system to pull it? That is called cross-set velocity. At what velocity it will pull the material? How much in the Hindalco they are giving? I forget exactly. You remember? Cross-set velocity.
Gauge length data.
Gauge length data. How much it was?
50 mm.
50 mm. 50 mm or 50 mm? Gauge length.
50 mm.
छोटा वाला, but how much? 50. Anyway, Anyways, so just forget about that. Just remember, with a particular velocity, it will pull the material, and that is called cross-head velocity. Some people call cross-head speed also. Both are fine. What about yield strength now? So that means you understood strength means it is resistance to plastic deformation. In the simple term, you can say resistance to plastic deformation is called strength. Because you are pulling it, but the material don't want to elongate. It will resist it. So that resistance is nothing but your strength, right? So that is the reason why ductility is always opposite to strength, or you can say strength is always opposite to ductility. If a material is highly ductile, strength is very less. If a material is less ductile, the strength is very high. But it doesn't mean if a material is completely brittle, you can say it is having high strength. It is wrong, actually. Sometimes they will ask to draw a stress versus strain curve for a brittle material and for a ductile material. Can you draw it in one single curve? Huh? See how you can distinguish a brittle material and ductile material. Huh? By again you need to check the percentage total elongation. I told you need to check the percentage total elongation. If the percentage total elongation is less than 5%, then it is brittle. If the percentage total elongation is more than 5%, you can say it is a ductile material. More it is high, more ductile it is. So the baseline is 5%. So total percentage elongation should be above 5% to become a brittle material. If it is less, that means it will fracture quickly without any gross plastic deformation. Okay. So these are some important points you have to remember. Fine. So at this point, what exactly happens? Plastic deformation starts, or people call onset of plastic deformation. Up to here, there is no permanent deformation. Because if you release the load, again it will come back to its original dimension, right? But beyond this, it will start deforming permanently. So this is permanent deformation. So what is the definition of yield strength now? Can you tell me how you can define? Strength means resistance to plastic deformation. What is yield strength? So that value of stress when the plastic deformation starts, or that value of stress where onset of plastic deformation happens. Very simple words. Just remember the diagram and you can tell easily. So similarly, from this point to this point, something is happening inside the material. What exactly happening? Strain hardening. Very good. Strain hardening. That is the reason why the stress is increasing. See, the value of stress is increasing from YS to UTS, and that phenomena is called strain hardening. And what is the reason of strain hardening? Because of generation of dislocation. Dislocation, whatever it is there, it multiplies to 1,000 times or more than that. Million number of dislocation may generate. You cannot say. It depends upon how much stress you are applying. Okay. So due to generation of lot of dislocation, material becomes strain hardened. So your stress value also increase. Is it fine? So from here to here, that is called strain hardening phenomena. Your stress will be more. Is it fine up to this? Now, how you can define UTS? What should be the definition of UTS? Maximum? Yeah. Yeah, maximum value of stress which a material can withstand. In simple words. Because beyond that it cannot withstand the stress. So, onset of necking, yeah, you can say it like that also, no issue. But it is better to say maximum stress a material can withstand. Onset of necking is fine, no issue. Okay, fine. After this, what happens? You see, the value of stress is going down. That means strength is decreasing again. Why the strength will decrease? Dislocation is increasing. Strength should be more. But why again it is decreasing? Strength increases, reach to a maximum value, again it decreases. Why? He already told the answer. Necking will start. What exactly necking means? Can you tell? हाँ पतला होगा, but पतला होगा means the cross sectional area will reduce at a particular location. That is the failure site actually. At that point failure will occur. In the gauge length, right? The gauge length is elongating, right? It doesn't mean the cross sectional area will reduce here or it will reduce here. It is uniformly reducing everywhere. But at a particular location, there will be more reduction in cross sectional area will happen. For example, just imagine this is the cross sectional area of the gauge length. Okay, up to this. So what will happen further? It will become long like this, but it will become thin like this. Okay. Further it will become longer. It will become more thinner. Cross sectional area is reducing, but elongation is increasing. But a time will come, what will happen? Specifically maybe in this region. Okay. Specifically maybe in this region, there will be more reduction in the cross section area compared to other area. So this will be like this, for example. Let's see. So this is called necking. This portion is called necking. Formation of a neck, like you have a neck, same thing. Because this diameter, this thickness is more, and body thickness is also more, but the neck thickness is less. So along a particular location in the gauge length, it happens. The cross sectional area will reduce to a large extent. So that means what will happen? It cannot withstand the load because other region is thicker. They can withstand the load, whatever you are applying on the material. But the area which is very less, it cannot withstand that load. So failure will start from there only. And finally the material will get rupture. It will become two part. Fracture. That is called FS. So this is the reason of strain hardening and this is the reason of necking. So necking starts from here. That's why the strength is going down. And finally a point will reach, they will become into two parts like this. So this is the final. So if you measure now entire cross sectional area, see this area under this curve, this is called toughness. But this is not the right way to measure the toughness. To measure the toughness, you have to do impact test basically. There is a test called impact, Charpy impact test. It is there in our lab, mineral processing lab. The machine is there. Any idea you have how we do Charpy impact? Any idea you have? Material testing started or just started? Okay, sir, मैं teach you. Who is what is the stage? What is this reason? Can you tell me? This blue. What is this blue reason now? This is resilience. Actually, the point is not this one. Okay, let me. You can draw like this. Sorry. This. Sorry. This one. This me. So this is the point. This point. Okay, and the point. So, suppose this is a stress versus strain curve for aluminium, for example. Very ductile. Aluminium is FCC, very ductile. For copper is also. But if you are talking about mild steel now, so the stress strain curve will remain same or it will become different. It will become different somewhat. Okay, fine. But if it is aluminium, for example, it is FCC, can we really determine the YS by doing tensile test, simple tensile test? If the material is highly ductile, can we measure the YS? Directly. No, we cannot directly measure the ys. Why? Because there will be no such point like ys I have shown you. You have to do proof stress at that time. You have to find out the proof stress. What is how much? That is 0.2% elongation. Or 0.2% strain actually. Suppose this is the point. Okay, fine. Let me erase it. See, if this is the curve, there is no ys. You cannot determine it. Fine. So what can be done? You need to go in this direction first and take point, because this is the strain axis, right? So you have to measure the 0.2% strain. Suppose 0.2% strain is this one. Let it be this distance. You need to draw a parallel line like this. To what? To your main curve. This is your main curve. So you need to draw a parallel line like this up at this 0.2% elongation or 0.2% strain actually. So it will definitely cut the line here. So this will become ys. This is not an exact diagram, but you understood this one. The question is, sometimes they ask, if you have a mild steel, you can easily determine ys. The curve will show you the point for yield strength. But if it is pure aluminium, if it is pure copper, there will be no point at all. So how you can determine the yield strength? Then you have to say, we need to go for 0.2% strength. From there, we need to draw a parallel line to the main axis, main stress strain versus axis, right? And it will cut the curve. Where it will cut the curve, exact that point is ys. Is it fine? Okay. Okay, what is toughness? But how we can define a toughness of a material? Energy absorbed before fracture. Fine. That means how much a material is absorbing energy before fracture happened. If it is absorbing more energy, that means the material has more toughness value. If it is absorbing less energy, it has less toughness. So that is the reason why we measure the area under the curve in the stress versus strain curve. Because if you multiply, it will give you energy actually. But okay, fine. There are other mechanical properties that is called hardness. So what is the definition of hardness? How you can measure a hardness? See, hardness definition is again resistance to plastic deformation. Same. The definition for strength and hardness are nearly same. If you see in normal world, resistance to plastic deformation is strength. Resistance to plastic deformation is also called hardness. But what is the difference? Basically, we measure the hardness of the surface, right? But strength will talk about the whole material property. Sometimes also hardness will talk you about the entire bulk property. That is called bulk hardness again. But the difference is, to measure the strength, you have to do tensile test. But to measure the hardness, you have to do indentation test. Indentation. Sir will teach you in the lab. You have to put an indenter like this. Suppose you have a material, you try to bring an indenter like this. Material is there, you put an indenter on this. The indenter is harder than the material. That should be condition. Maybe that will be made up of some special steel, or maybe made up of some diamond. It should be harder. So what will happen when you press the indenter on the surface? It will give an indentation mark, and in that indentation mark you can measure the depth or you can measure the diameter basically, and finally you will get the hardness value, right? So if the depth of indentation is more, it is more harder or more softer material? More softer material, very good. If you are measuring the diameter of the indentation, if the diameter is more, it is ductile material or harder material? Ductile material, so very good. So you understood. So it exactly is saying resistance to plastic deformation, but it is measured by doing indentation. So strength is nothing but resistance to plastic deformation measured by doing tensile test, but Hardness is the resistance to plastic deformation measured by doing indentation. Similarly, you take a piece of diamond and you take a piece of your copper, for example. You rub it. So what will happen to the diamond and what will happen to the copper after rubbing the diamond over it? The diamond will scratch the copper, right? But there is nothing will happen to the diamond. So that means diamond is more harder, copper is softer, right? So some people, that's why also called hardness is nothing but resistance to scratch. In simple words, if there is a deep scratch, that means it is more ductile. If a scratch is very thin, it is somewhat harder. Okay, you understood how I am correlating? Fine. So either resistance to plastic deformation or resistance to scratch is called hardness. Any other properties we have? Okay, fine.